It's amazing, isn't it? How many smart devices we use every single day now. And I don't mean just like, simple commands or setting a timer. I'm talking about real language understanding.
Right.
Like, we've got instant translations that actually do a pretty good job with nuance.
Mm.
We've got those chatbot things that are popping up everywhere. Some of them can answer really complex questions.
Yeah.
Even systems that can summarize like huge, complicated documents for you. It really feels like, in a way, we've kind of crossed this line where machines aren't just processing information. They're actually starting to, I don't know, kind of grasp the meaning behind it.
Yeah, I think that's a really key point. It's not just retrieving information anymore. It's like you said, it's about comprehension. And that's really what makes this whole area of applied text analysis so interesting.
Yeah, and that's exactly why we're doing this deep dive today into applied text analysis with Python, the book by Benjamin Bengfort, Rebecca Bilbro, and Tony Ojeda. Think of this as your, like crash course on the fundamentals of how we can get machines to like truly understand and process language using Python, of course.
And this book's really great because it takes a really practical approach. It's really geared towards like giving the tools to developers and data scientists so they can build what they call language-aware data products, using Python, of course, and machine learning techniques. So our mission today is to really distill the key takeaways from this book and, give you that solid conceptual foundation without getting bogged down in the super technical, weeds.
Yeah, exactly. We want to highlight those big aha moments that show you how you take just raw text and you turn it into something a machine can actually analyze.
Yeah.
And then use that to build some pretty amazing intelligent applications. So, first things first, right? What are some of the big challenges, but also maybe the opportunities that we're facing when we try to get computers to understand something as, I don't know, subtle and constantly changing as natural language?
Well, the authors did a great job of addressing this right up front. They say, look, natural language is inherently messy,
Right.
right? We're redundant, we're ambiguous, and our perspective colors everything we say. And then on top of that, language is always evolving. They even mentioned the Emoji Dick project. Have you heard of that?
No, I have.
It was this really cool project where they tried to translate Moby Dick, the entire book, into emojis, which I think is a really good illustration of, how we're constantly adapting language. And even the meaning of individual emojis can change. They use the pistol emoji as an example. Its meaning has really shifted over time because of, cultural shifts. So it really is a moving target.
It's like trying to, solve a puzzle where the pieces are changing shape while you're working on it.
Exactly. But, amidst all this complexity, there's this really crucial underlying idea that the book emphasizes, and that's the predictability of text. That's really the fundamental hypothesis that makes applying machine learning to language even possible. They even introduce this term perplexity, which is essentially a measure of how surprised a language model is by a given piece of text.
Okay.
So the lower the perplexity score, the less surprised the model is, meaning it's doing a pretty good job of picking up on patterns in the language.
So even though it seems so chaotic, there's still some underlying order there that machines can actually learn to recognize.
Right, that's the key insight. And the book really points to this shift in focus that's happening in the field. We're moving away from, very theoretical linguistics and statistical models and more towards a very applied focus. So how can we actually build these text analysis models and deploy them within, software applications? That's really what this book is all about.
Okay, so we have this, this complex thing called language, but there's some order in it. How do we even approach analyzing this? Systematically, what's the general process?
So the book lays out this model for text analysis, and it's actually very similar to the, traditional machine learning workflow. It's essentially a search for the best model, and by that they mean the optimal combination of, features, which are those characteristics you extract from the text, the algorithm you use, and the specific settings for that algorithm, which are called hyperparameters. And then this model is trained on a data set, which in the world of text analysis, we call a corpus.
So it's kind of I don't know, finding the right ingredients and the right recipe, the model, to bake a perfect loaf of bread, which would be the analysis, using a specific batch of flour, which would be the corpus.
Yeah, that's a really great analogy. And this whole process involves a few key stages. So first, there's corpus construction and management.
Okay.
That's all about building and organizing your collection of text data. Then you have feature extraction and preprocessing. And that's about converting the raw text into a numerical format that machines can actually understand.
Mm-hmm.
And finally, we have techniques for classification, which is basically categorizing the text and clustering, grouping similar texts together.
Got it. So we're taking this messy world of language, we're translating it into this very precise world of numbers,
Yeah.
and then using those numbers to find some patterns.
Exactly.
Now, the book talks a lot about language-aware data products. What exactly makes them different?
So these are basically user-facing applications that can, truly interact with and understand text. They take text as input, they parse it, which means like breaking it down into its components.
Yeah.
They do computations on those parts, and then they give you back a meaningful result, something tailored to, what you were asking. They give some really good examples in the preface, like machine translation tools and chatbots.
So it's like any application that goes beyond just showing you text, but actually does something intelligent with that text based on what it means.
Exactly. And they actually go into this really detailed breakdown of the build phase of these products.
Okay.
It's basically a pipeline that takes raw data, ingests it, stores it as a corpus. Then it goes through all this cleaning, normalization, and crucially, transformation into vectors, which are those numerical representations we were just talking about.
Right.
And finally, you train your models on these vectors. That's what gives the application that ability to understand and respond to new data.
Okay, so it's like an assembly line built specifically for understanding language.
Yeah, you could think of it that way. And to really get into how these data products are designed, they talk about this idea of the model selection triple.
Okay.
And this breaks down the concept of a model into three parts. The model family, so that's like, linear models or neural networks.
Mm-hmm.
Then you have the model form, which is the specific combination of features, algorithm, and hyperparameters that you choose.
Okay.
And then finally, the fitted model, which is essentially that model form after it's been trained on your data and is ready to make predictions. And these language-aware data products are basically built on top of, many of these fitted models all working together.
Right. So it's like this, this complex orchestra of models all contributing to like making sense of the text.
Yeah, that's a good way to put it.
So at the most basic level, how does a machine actually start to understand language? Like what's the underlying mechanism?
Well, the book explains that a key aspect is using context to infer meaning. Right. Think about how we as humans process language. We rarely interpret words in isolation.
Yeah.
So language models try to do the same thing. They might take an incomplete phrase and try to predict what word is most likely to come next. And that really underscores, that basic idea we talked about the predictability of text.
Right.
There are patterns there.
And they have this really interesting early example in the book, right? Something about gendered word lists.
Oh, yeah. They talk about analyzing text by creating these lists of words that are stereotypically associated with, males, like he, him, father.
Okay.
And then words associated with females, like she, her, mother.
Right.
And just by counting how often these gendered words appear in a sentence, you can actually get a rough idea of whether that sentence is more likely to be about men or women, or both, or neither. They even give you some basic Python code for like creating these sets, male words and female words, and some simple functions like, genderize and count gender to do this very basic level of analysis.
It's pretty clever, actually, just starting with simple word counts. But the book obviously points out that there's a lot more to language than just, these kind of explicit gender markers.
Oh, absolutely. They stress that language carries information through things like tense and plurality. Like you could use that same counting approach to see if the language is mainly referring to the past or the present or the future. But it's not just those direct linguistic features, but also contextual features. And a big example of that is sentiment analysis.
Right.
Which is about, trying to figure out the emotional tone of a piece of text.
Mm-hmm.
Are they happy, sad, angry?
I remember them saying that just having a list of like positive words and negative words isn't really enough for accurate sentiment analysis. Why is that?
Yeah, because that approach is way too simplistic. It completely ignores things like, sarcasm or the fact that the meaning of a word can completely change based on the words around it. Like, saying not good is clearly negative. But if you just have a list of positive and negative words, you might just see the word good and miss the not.
Right. Context is so important. So how do we go beyond just counting individual words? Like how do we start to capture that context?
That's where the idea of language as data really comes in.
Yeah.
And one of the foundational techniques they discuss is the bag of words model.
Okay.
And basically, in this approach, a piece of text is represented just as a collection of the words it contains. You ignore the grammar, you ignore the order, but you keep track of how many times each word appears.
So it's like, taking all the words out of a document, dumping them into a bag, and then just counting how many times you see each one.
Yeah, exactly. And then they talk about ways to build on this basic idea, like enneagram analysis.
Okay.
So instead of looking at just individual words, enneagrams consider sequences of words.
Okay.
So a binagram looks at pairs of words, a trigram looks at 3 words in a row, and so on. And this helps capture some of that local context, like peanut butter as a bigogram means something different than just peanut and butter on their own.
Right.
So if you have withdraw money at the bank versus fishing by the riverbank, the bigograms and trigrams would help the system figure out which meaning of bank is intended.
Right, yeah.
But I'm sure you can imagine the number of possible n-grams can get really huge really fast.
Yeah, that makes sense. So the longer those sequences of words, the more possibilities there are.
Exactly. And the book points out that while n-grams can be great for context, if you go too high with the n, you end up with a lot of sequences that are either very rare or just don't make any sense.
Right, yeah.
So it's about finding that balance. They also touch on the idea of structural features. That's where computational linguistics comes in.
Okay.
Like helping us understand the grammatical structure of sentences. But what about the actual meaning of the text? That feels like the holy grail of understanding language, right?
Yeah, that's the big question, isn't it?
It is. That's semantics. And as the book rightfully acknowledges, that's something that's still a huge challenge to really capture computationally.
Right.
They talk about the idea of using templates, like subject-verb-object structures, to help build what they call ontologies, which are basically structured representations of knowledge.
Okay.
But creating those usually requires a lot of domain expertise.
Yeah.
And it doesn't always scale well. So really grasping meaning is still this frontier that we're still working on.
Right. So it's like we can do a lot with patterns and structure, but that deep understanding of meaning is still tricky.
Exactly. But they do point out that even if we can't get to that full semantic understanding, techniques like graph analysis can still be really useful, like representing words and their relationships as a network.
Okay.
You can analyze those connections and, see which terms are more important within that network.
Interesting. So we've talked about the nature of language and some ways to represent it as data. But to do any real analysis, you need a lot of text. Right. Okay. How do you go about building that collection?
So that brings us to the idea of building a custom corpus.
Okay.
And the book really stresses that for good text analytics, you need a large, robust, and this is a key domain-specific collection of text.
Right.
Like if you're trying to analyze, medical research papers, having a bunch of social media posts isn't going to be very helpful.
Right. Garbage in, garbage out, as they say.
Exactly. But then the question is, how do you actually structure and manage these potentially massive collections of text?
Yeah, that's a good question.
So they outline a few different strategies. You can store each document as a separate file.
Okay.
Maybe organize them into folders based on categories.
Mm-hmm.
They also mention using databases, although they seem to prefer file-based approaches because they're generally simpler, and file compression can be really effective.
Makes sense.
The important thing is to have a consistent structure so your Python programs can easily find and access the data. And then they introduce the concept of a corpus reader.
A what?
A corpus reader. Think of it like a programmatic interface to, read, access, and even do some initial pre-processing on the documents in your corpus.
So instead of me having to open up each individual file and read through it, the corpus reader gives me a more organized way to access all that data.
That's exactly right. It handles things like, finding where the document files are, efficiently streaming the data so you don't have to load everything into memory at once, and even applying some basic pre-processing steps.
Okay.
They give an example called categorized plaintext corpus reader, which is perfect if you have a bunch of plain text files that are organized into categories. Like they use this example of movie scripts categorized as, Star Wars or Star Trek.
Oh, cool.
And they even show you how to define these regular expressions that can automatically figure out the file identifiers in their categories.
Mm-hmm. So if I had a bunch of customer reviews and they were neatly organized into folders for different product lines, I could use something like that to easily access and, categorize them for analysis.
Yeah, exactly. And they also mentioned that for more complex formats like HTML documents or stuff stored in a database, you might need to write your own custom corpus reader.
Okay.
But the basic principles are the same, providing a structured way for your program to work with the text.
Okay, so we've built our corpus. Now we need to get it ready for the actual machine learning, right?
That sounds like it involves some transformation.
Yeah, that's a good way to put it. Corpus transformation is all about preparing the text for analysis. And the book goes into some key steps.
Okay.
Segmentation, which is breaking down the text into meaningful chunks like paragraphs and sentences. Tokenization, which is splitting those sentences into individual words or tokens. And part of speech tagging, where you basically label each word with its grammatical function, like noun, verb, adjective.
Right. And they point out that a single word can have different parts of speech depending on the context, like building can be a noun or a verb.
Yeah, that makes sense. So it's like we're taking this raw text and adding these layers of linguistic information, breaking it down and labeling everything.
Exactly. And they show how you can create a tokenized method in Python using NLTK, the Natural Language Toolkit, to do all of this.
Okay.
They use functions like postegg, sent tokenize, wordpunct tokenize, all that good stuff. And they also point out that, as you add all this information, your data can actually get quite a bit bigger.
Right.
So they recommend using Python's pickle method to efficiently save the pre-processed corpus.
Okay. Pickle.
Yeah, it's basically a way to serialize the Python data structures into a format that's much faster to load and store, kind of like, preserving food in jars, but for data.
I like that analogy. So once we've pickled our corpus, how do we actually retrieve it and use it?
You'd use a special reader called Pickled Corpus Reader. It's specifically designed to load those pickled structures quickly so you don't have to redo the tokenization and parsing every time.
Gotcha.
Which can save a lot of time, especially when you have these huge corpora.
Right.
So the initial pre-processing might take a while and could benefit from parallel processing, but once you've done that and pickled it, everything else becomes much faster.
Okay, so now we have our pre-processed corpus, maybe even pickled for efficiency. Now the big step is to turn those words into numbers that the machine learning algorithms can actually work with, right? And that's where text vectorization comes in.
Exactly. Text vectorization is about representing words and documents as numerical vectors.
Okay.
And the book covers several different techniques. The simplest one is frequency-based encoding,
Okay.
where you just count how many times each word appears in a document. They use an example with NLTK's word tokenize and the snowball stemmer to normalize words to their root form.
So essentially, a document becomes a vector where each dimension represents a unique word. And the value in that dimension is just the count of that word in the document.
Sounds pretty straightforward, but I think I remember them mentioning some limitations with this approach, right?
Yeah, they talk about one-hot encoding, which is where you represent each document as this binary vector.
Okay.
So if a word is present, its position in the vector gets a 1, otherwise it's a 0. And while that can help with some issues of just using raw counts, it completely ignores grammar and the order of words. Plus, natural language tends to follow what's called a long tail distribution,
Right.
where a small number of words appear all the time, but there's this huge number of words that only appear very rarely.
Right.
So that can create these really sparse and high-dimensional vectors. They have an example using GenSim to show this one-hot encoding.
Right, because the number of unique words could be massive, and it seems like this approach treats every word as completely separate, right? Like trying and try would be as different as trying and bicycle. Exactly. To address that, they introduced TF-IDF, which stands for Term Frequency Inverse Document Frequency.
Okay, I've heard of that.
This technique tries to capture not just how often a word appears in a document, but also how unique that word is across the entire collection of documents.
Okay.
So a word that appears a lot in one document but is rare overall will get a higher weight.
Got it.
And a really nice side effect of TF-IDF is that it naturally downplays the importance of those super common words, the S and AS of the world, because they'll have a low inverse document frequency.
Right, because they appear everywhere, so they're not really that helpful in distinguishing one document from another.
Exactly. But what about even more sophisticated approaches to vectorization?
Like what?
They also talk about distributed representations, which are sometimes called word embeddings.
Okay.
And these are pretty different. Instead of focusing on individual word counts, they try to represent words and documents as points in a continuous lower dimensional space. The idea is to capture semantic similarities. So words that are used in similar contexts will have vectors that are close to each other.
Interesting.
It's more complex and computationally intensive, but it can be really powerful if you're working on tasks where understanding the meaning and relationships between words is essential.
So in this approach, trying and try
Yeah.
would probably have very similar vectors, right?
Yeah, exactly. And, the vectors for king and queen would likely be closer than the vectors for king and bicycle.
That makes sense. So it sounds like there's no one-size-fits-all approach here. The best technique really depends on what you're trying to do with your analysis, right?
Exactly. You have to choose the right tool for the job.
Okay, so we've got our text vectorized.
Mhm.
I imagine this is just one part of a larger process, right? How do you manage all these different steps in a clean and organized way?
That's where scikit-learn pipelines are really helpful. They allow you to chain together these different data transformations, like our normalization and vectorization steps, and then the actual modeling phase, all into one neat workflow. They emphasize this concept of the transformer interface, which has these fit and transform methods. So the fit method learns from your training data, and the transform method applies those learned transformations to both your training data and any new data you want to analyze.
So it's like having I don't know, a recipe where each step from prepping the ingredients, normalization, to the actual cooking, vectorization, and then plating, modeling, is clearly defined and executed in order.
That's a perfect analogy. They give an example where they combine their custom text normalizer with a Gensum vectorizer and a pipeline, and then apply a Bayesian classification model. And this makes your code much more organized, reproducible, and easier to test and refine. They also mention this thing called feature union, which lets you apply multiple transformations independently and then combine the results.
So I could, for example, extract both Ngram features and TF-IDF features separately, and then combine them before feeding them into my model. That sounds pretty flexible.
Yeah, it is. Pipelines and feature unions are really key tools when you're building these text-based applications.
All right, so we've laid all this groundwork. Now we can start building some intelligent systems. Let's talk about classification for text analysis. What's the main idea here?
Classification, when it comes to text, is about assigning predefined categories or labels to documents based on what they say.
Okay.
It's supervised learning because you have this target variable, the category you want to predict, that you've already labeled in your training data.
Right.
And the book has some really good examples, like automatically categorizing product descriptions, analyzing the sentiment of reviews, figuring out the topic of a news article.
So if I had a bunch of customer feedback, I could use classification to automatically tag each piece as, like a complaint, a suggestion, or a compliment.
Exactly. And they point out that a lot of language-aware data products are actually built on top of, multiple classification models working together.
Interesting.
So like a product recommendation system might use classifiers to figure out the product category, the target audience, and even the quality of reviews.
It's like building this more complex intelligence from these simpler categorized components.
That's a good way to think about it.
So what are some common models we can use for text classification?
They mention naive Bayes as being really useful. It's what's called an online model, meaning it can be updated as you get new data without having to retrain the whole thing from scratch.
Okay.
It's often used in things like spam detection. They also stress that there are a ton of other classification models, from simple linear models to more complex nonlinear ones, and even deep neural networks.
Right.
The key thing is that when you're using libraries like scikit-learn, they all follow a similar workflow. Train on your labeled data, and then use the trained model to predict labels for new text.
Makes sense. But how do you know which classification model is best for your specific problem?
That's a great question. And that brings up this concept of the bias variance trade-off.
Okay.
So more complex models might fit the training data really well, but they might not generalize well to new data. So you want to find that balance. And the main way to do that is with cross-validation.
Okay.
That's where you basically divide your data into subsets, train on some, and test on others. It gives you a better idea of how your model will actually perform in the real world.
So it's like testing your recipe on different groups of people to make sure it has broad appeal, not just people who are already familiar with your cooking style.
That's a great way to put it. And how do you actually measure how well your classification models are doing?
Right. That's important.
So the book goes into some key evaluation metrics.
Okay.
Accuracy, which is just the percentage of correct predictions overall. But they warn that accuracy can be misleading, especially if some categories have way more examples than others.
Yeah, that makes sense.
So they also talk about precision, recall, and the F1 score. And then they have this thing called a confusion matrix.
Okay, a what?
A confusion matrix.
Right.
It gives you a breakdown of, which classes the model is getting right and wrong.
Okay.
So it's like a deeper dive into how the model is actually performing.
So it's not just about whether it's working, but how it's working and where it might be struggling.
Exactly. And by comparing all these metrics across different models and different settings, you can figure out which model is really the best for your specific task.
Got it. So classification is about putting text into these predefined boxes.
Yeah.
What if you don't have those boxes? That sounds like it would involve clustering.
Yeah, you're right. Clustering is this unsupervised technique where you're trying to discover natural groupings or clusters of similar documents.
Okay.
And they use this analogy of having this big, unsorted pile of documents, and you're just trying to organize them into meaningful groups based on their content.
I like that. So we're letting the data tell us what the groups are, not the other way around.
Yeah.
How do you even determine if two documents are similar for clustering?
That's where distance metrics come in.
Okay.
They talk about several, like Euclidean distance, which is just like measuring the straight line distance between 2 points.
Right.
Edit distance, which measures how many edits you need to make to turn one string into another.
TF-IDF distance, and cosine distance, which measures the angle between two vectors. And cosine distance is actually really well suited for text because it focuses on the similarity of direction rather than magnitude.
Got it.
So we represent documents as vectors, and then we use these distances to figure out how close they are in this multidimensional space.
Yeah.
And those closer vectors are more likely to be clustered together. What are some of the actual algorithms used for clustering?
They talk about two main types: partitive clustering and hierarchical clustering.
Okay.
In partitive clustering, you're basically dividing the data into a fixed number of groups.
Okay.
And a popular algorithm for that is k-means, where you decide how many clusters you want, k, and the algorithm iteratively assigns documents to the nearest cluster.
Okay.
Hierarchical clustering is different. It creates this like tree-like structure that shows the relationships between clusters and different levels. And for that, they talk about agglomerative clustering, which starts with each document in its own cluster and then keeps merging the closest ones until you have a single cluster or you reach your desired number of clusters.
So k-means gives you these separate groups, while hierarchical clustering shows you how those groups relate to each other, like who's closer to whom.
Right. But what if you want to find the hidden topics within a collection of documents?
Oh yeah, that's a different challenge, isn't it?
It is, and that's where topic modeling comes in.
Okay.
They discuss three main approaches: latent dirichlet allocation, or LDA, latent semantic analysis, or LSA, and non-negative matrix factorization, NNF.
Okay, a lot of acronyms there.
Yeah, there are. But basically, LDA is this probabilistic model that sees topics as distributions over words and documents as distributions over topics. And one interesting thing about LDA is that it allows for what's called topical fuzziness,
Okay.
meaning a single word can belong to multiple topics.
So, like, a word could appear in discussions about both technology and finance if those topics overlap.
Exactly. And they mentioned that LSA is sometimes better for like longer documents with lots of different words, while LDA and NNMF might be better for finding more concise and easily interpretable topics.
Okay.
The book actually shows you how to implement LDA using both scikit-learn and GenSim, and how to figure out what those topics are by looking at the words that are most likely to belong to each one.
So it's like you run the algorithm, and it spits out these groups of words that represent the main themes in your data.
Pretty much.
So clustering and topic modeling are these powerful tools for finding hidden structures and making sense of data that isn't already labeled, right?
Exactly. And they even point out that you can use these techniques to help in label data for supervised tasks like classification.
Interesting. We've talked a lot about individual words and their frequencies, but we also touched on the importance of context earlier. How do we move beyond this bag of words idea to capture context more effectively?
Yeah, that's a great point. And the book addresses this by diving into what?